Good morning, good afternoon, or good evening from wherever you're joining us. Welcome to the FCIA Fibre Channel Industry Association presentation of NVMe over FC. This is a deep dive into the protocol, architecture, and use cases. I am your host and moderator, David Rodgers. I am very pleased to present our panel today. Some very good experts in the area. We'll be led off by Mr. Kamal Bakshi, a technical director at Cisco, and someone who's very ingrained into the architecture of NVMe, followed by Nishant Lodha from Marvell Semiconductors, a director of the Emerging Technologies Group there. And we'll be wrapped up with Mark Jones, technical marketing at Broadcom, and FCIA President Emeritus, and a longtime proponent and advocate of the Fibre Channel protocol in our market space. A little bit about the Fibre Channel Industry Association. We are, in fact, the nonprofit international organization of manufacturers and systems integrators, developers, vendors, and industry professionals and end users promoting the Fibre Channel protocol and fabric in all of its permutations. A little bit more about us. Fibre Channel Industry Association is 25 years old, again, promoting the Fibre Channel technologies across the various different implementations and deployments. The FCIA is led by industry-leading companies. You can check us out on our website and see more about us there. Currently, and this is based on some information we have from the industry analysts, and Mark can present more about that later on if we're interested, but 160 million FC ports have been shipped since 2001. We see about 8 million ports shipped annually, and roughly 35 to 38 million over the past 5 years. Our revenue and our excuse me, I got a frog in my throat this morning. I apologize. And information from Quillen Research, $50 billion in Fibre Channel revenue. Pretty sizable number for the last 25 years. And I've already spoken to the 35 million ports. But adapter and switch ports, 160 million of them. We will be getting into our agenda here. We will be having an overview of the NVMe architecture, and then NVMe and FC and how that lays out, adoption and virtualization use cases, and then getting into performance. And with that, I'm going to hand this off to Mr. Kamal Bakshi. And Kamal, take it away.
Thank you very much, David. Very glad to be here at FCIA. And the goal, as you said, is educate people on Fibre Channel storage technologies. What I'm going to do in the next 30 minutes is here, as you talked about, Fibre Channel is a $50 billion. There's a lot of investments already done on it. And what are we talking about here? We're talking about the storage transport here. Fibre Channel is the gold standard for storage transport. If you take IBM Ficon, which is also on top of Fibre Channel, and all the SCSI on Fibre Channel today, that covers you over 90% of all any mission critical application anywhere in the world goes on the Fibre Channel. There are other two transports. There's an Ethernet in there, which is more primarily for getting from point A to B for the internet. And and then there's an InfiniBand, which tried to replace Fibre Channel and Ethernet and PCIe and all that, got very complex in there. Even though the title says it's a deep dive into Fibre Channel, but as we all know, as a storage admin, that we never have to look inside the Fibre Channel packet and frames, unlike other transports, because it's all automated. So that's the beauty of the Fibre Channel, is it's totally automated. All the complexities which I'm going to show you today, deep dive into architecture, you never have to touch about it. You don't even have to know about it. Is that what is going on underneath? You plug your host into the fabric, SAN fabric, the storage plugs in there, and automatically there goes, they discover each other, and all those things happen automatically. That doesn't happen in any other transport world. You have to have some kind of a software controller defined, which Fibre Channel from day one is built into it. All right, so let's look into it. And just to talk about topic today is the NVMe. As everybody knows that SCSI protocol has been historically the transport protocol, the storage protocol. And when the flash came along, the SCSI was a little slow on it. So there comes the NVMe consortium, and they try to optimize this block level protocol just for the flash. Minded that the rest of the other things, disks and everything else, runs on the SCSI. So it's only flash, a block flash in there. Even though there is some disk technical proposal in NVMe committee to make it disks also go on the NVMe. NVMe trademarks are registered trademarks. It's a LLC company. They like to, when they use the terms, they like to say that you use those proper terms. I took this page out of the NVMe consortium page. This is how they represent different protocols, especially if you notice the NVMe / that tells you what transport protocol you're going on. PCI is the native transport protocol for NVMe because it sits inside the bus computer architecture. And then, when you go outside of the computer for NVMe access, then you have Fibre Channel and TCP and the RDMA protocols in there. Now, the difference between NVMe / Fibre Channel versus that's the NVMe consortium that defined the protocols. The beauty of them is that they went to each transport original designers and asked them how to map NVMe inside that protocol. So for Fibre Channel, they went to T11 and asked them how to map NVMe on top of the Fibre Channel. And T11 came out with the standards, and they named the standards FC-NVMe-2. So that's just a little nomenclature about it. Now, if I talk about where does the storage got started? Well, storage got started with IBM, right? Of course, the mainframes, huge mainframes, right? Back in 60s, System 36, 360. IBM started the huge DASIs, right? The huge disks in there. And they had the way they stored the data, just like we store the data on the disk today with LBA. They store the data with CKD, right? The count key data tracks and all that. And the commands, instead of using SCSI and all that, they use CCW commands, channel command words. Because in IBM world, there used to be channel and IO controller. And all that is called single byte command control sets. And then when Fibre Channel, those guys mapped all those command sets into the Fibre Channel because they early on they used to do SCON protocols, and then when they were not able to increase the speed on the SCON fiber. Before that, there was a copper bus and tag, so they chose Fibre Channel as a transport, and that's mapping is called FCSB6, so single bytes mapping in there. And then came along the Unix workstations and mini computers. So SCSI was invented to do the storage protocol. We all familiar with the ribbon cable and all that. That becomes serialized. And then IBM came along with their protocols, and then they moved in there. Now, as with the flash, we had to have a new protocol, NVMe, and that's where it came up, right? So Fibre Channel SCSI and Fibre Channel NVMe both are the standards for the storage today, and they both coexist together, and that'll become very clear when I talked about it. NVMe has been going on since 2008. What we're talking here is that how those guys try to map PCIe bus inside the NVMe architecture. They replaced the SCSI commands with NVMe new commands. They required just a minimum sets of command. They took the existing transports. Now, that's the difference between iSCSI and other protocols, that NVMe from day one is tracking or is transport agnostic. PCI is the native interface, local interface. And when you go on the network, Fibre Channel is the gold standard, as I said, on the storage transports. But NVMe allows you to do other things for high performances. You can do InfiniBand. And if you just don't need mission critical, you may experiment with NVMe TCP and all that. But for the enterprise storage and everything is Fibre Channel. Current existence is NVMe 2.0. This in NVMe 2.0, if I break it down, it has like 4 different categories in there. There's a management specs in there. There's a base spec, which is common to all the specs. Then there is some specific IO commands. There are different NVMe command sets. Started out with just basic command sets, and then they came out with something called zone name command set, then the key value command sets, and anything what they add more, they will keep adding on those top of that. And then this is the beauty of the NVMe, is that it's the transport agnostic. And it talks about 2 different type of a transport structure models. One is a shared memory based model. That means it's in the PCI bus and everything is mapped into the memory of the computer. And then second one is a message based. That means if you go into the transport like Fibre Channel or on the Ethernet, then it is a message based. That means you create a capsule, and I'll talk about how the submission queues and completion queue capsules are created, a fixed byte 64 and 16. And the goal here is that if you're doing any iSCSI or anything, that'll be replaced with TCP. But or if you're doing early on any ICER or any InfiniBand thing, that will be done with NVMe, InfiniBand, or NVMe over UDP with Rocky. Or with the beauty with the fiber channel is that it coexists with NVMe and the existing SCSI protocols in there, and hardly there's any thing required within the fabric to upgrade anything. Of course, you need the drivers at the either end to get those NVMe thing. And I'll show you what are the benefits of moving towards NVMe. It puts more life into fiber channel. Fiber channel, as I said, is already very automated. And when NVMe technology came along, for other protocols, other transports, they have to come out with some kind of external methods to implement that. But with fiber channel, NVMe seamlessly got integrated with it without you even knowing it. So let's look at that inside of an NVMe architecture. And if you have any questions, please put it in the chat. In there, we have David Peterson and the whole team looking at it. They will be more than happy to answer your questions. Then I'll take the questions at the end also. And also, this whole presentation, as I'm talking, a lot of details in there will be posted on the FCI YouTube also. So end of the day today, you can go there and look at it and rewind the thing and check it out. So as I said, NVMe is flash is mapped into PCI bus automatically. So as fast as the PCI bus goes, that fast goes your storage access. And the NVMe commands are very, very simple commands. I'm just showing you a dozen of the commands in there, divided into 3 different categories. So there is an admin command. So that means anything to create the queues or to get the error log pages, identify what namespaces are, to get some features and all that. Those are all admin commands in there. Once all that is set, then the IO command goes in. IO commands are very simple, read and write and all that. There is an NVMe flush command. Don't get confused with it. I'm going to talk about a fiber channel, BLS, basic link services flush command also. But this is the NVMe flush command. All it does it takes the volatile memory and puts it back into the non-volatile memory. It flushes it out in there. Then there's a transport specific commands, connect, disconnect, that creates the NVMe queues and set properties and all that. That sets up your queues depths and all those things in there. As I said, or maybe I didn't say that, NVMe has like 64,000 queues, right? And then queues could be as deep as 64,000 also. But in real practice, by default, NVMe will go how many number of cores you have on your host or on your storage. That many queues will be by default created. If the host has a very advanced architecture CPU, it might create 128 cores and 128 queues. If the storage only has like an architecture with 8 cores, it might create 8. So during the negotiation, they will narrow it down to the lowest value in there. So very, very robust architecture. There's no controller in the middle, right? There's nothing needed. All NVMe control system is built on top of the NVMe flash systems. Now, if I look inside the architecture, let's open it up and deep dive into it. There's an adapter in there. This is the flash, which has NVMe controller sits on the flash. There's a flash translation layer, FTL, and then there sits your flash. We still write with NVMe or SCSI with the logical block addresses. That thing has not changed. It maps directly into PCI lane, so as fast as you go. And then this is a memory mapped IO, so that means the CPU memory is mapped. All this adapter or all this storage NVMe flash is mapped into the CPU memory. So when CPU is talking, it doesn't know whether it's talking to its memory or its flash because it's all memory mapped. That's where the base address registers comes in there, and that maps the controllers, the NVMe controllers memory into the CPU memory in there. Now, NVMe ports, that's where it talks about that behind the fiber channel ports. NVMe is done over the queue pairs. This is one of the beauty about it is, in fact, the idea came from the InfiniBand that queue pair concept is that if the host wants to talk to the controller, the host will go up and create on that particular controller an admin queue and IO queues. And admin queue is always the number 0, only one queue pair set, SQ and CQ. SQ is the submission queue, CQ is the completion queue. In submission queue, you set your commands. Completion is where the result comes up in there, right? And they are fixed bytes, 64-byte submission and 16 bytes completion queue in there. So they work very fast through the memory because of all these fixed bytes in there. And then host creates it. There's a one-on-one relationship between the host and the NVMe controller. Every time a new host comes in there, it will create it dynamically, a new NVMe controller. NVMe controller could be static or dynamic depending upon whether you want to maintain the states as you go to the next controller, the previous one, or the host can ask a static controller so the states are maintained and so forth in there. And I'll go into details of all these things in there. So if I break it down, NVMe architecture, it is the high level thing is that it's called NVMe subsystems, and it's qualified with an NQN name, fully qualified names. Within that subsystem, you can have multiple NVMe controllers. and each is identified by the controller IDs. And you can have a different type of a controllers. You can have a IO controller that only does the IOs. You can have a discovery controller that only does the discovery of the IO controllers, does not have any flash behind it. The purpose is just to tell the inquiring host what IO controller is here, so that you can get all your namespaces. In other words, a similar thing like what you get in LUNs and SCSI. And then, of course, there's an administrative controller there also. And I'm going to talk about IO controller. So this is how underneath it all works. Again, as I said in the beginning, it's all automatic. You don't have to worry about, as a storage admin, what's going on. But I'm just giving you a sneak preview underneath what happens. A host wants to talk some storage. It just enters some data, and it'll put it into the submission queue. There's the SGLs and there's the PRPs. If you're doing a PCI, then it's all pages in there, and this is scatter gather for the other transports. Anyway, so all the data gets mapped into the FC-NVMe driver is called in. And now what's going to happen is that we have to create the queues, because without the queues, NVMe is not going to talk. But now, how do you create a queues on the controller, on the storage array? It's a host responsibility to create the queue on that particular NVMe controller. And I said there could be multiple controllers because there could be multiple hosts coming in. So the first step in NVMe, which all happens automatically, again, it's all plug and play, is that the association is made. During this association, we'll say, are you capable of doing NVMe? If okay, all right, I'm going to create this association, some number in there. Within that, as I said, you could have thousands of queues. Admin queues is always 0. IO queues are other things, up to 65,000. Again, in IO queues, you only do like read, write commands, and admin queue is all the setting up the IO queues, and everything is started with admin queue. So each queue gets mapped into its own connection ID under that association. Now, this is very important because NVMe thrives on the parallelism. So when the packet goes out of the host, it has to go parallel. You cannot put it on a single exchange. In Fibre Channel, we set all the traffic through the exchange. So for every queue, there will be another XID generated. And that's how the parallelism goes over, not only within the architecture of the host and the storage array with parallel queues, but also on the transport. When it goes out, it gets its own exchange IDs. And of course, then you can load balance all those exchange, because a separate exchange. So exchange-based load balancing can happen if you have multiple paths to get anywhere. And then later I'll talk about it is if anything gets out of the sequence on those, there's a new commands, a new technology within FC-NVMe 2, second version, which is already out and people have implemented it, that the SLER, sequence level error recovery, very fastest way to get out of the error out of sequence. I'll explain that. So how does NVMe, the reason I'm showing you this PCI level or interrupt level low chart is not only NVMe architecture replaces the SCSI, but it looks around other improvements within the PCI world also. So here is the host trying to talk to the storage, trying to write. It creates an IO request. It will ring the doorbells. This is the concept of if the host wants to send something out to the adapter, it rings the doorbell. If the adapter gets something in from outside, it generates an interrupt to the MSI interrupt to the CPU in there. And NVMe supports all sorts of different interrupts in there. There could be a port-based interrupt. There could be, up to, with MXI, you can go 2K interrupts, a lot of things in there. All right, so now it goes ahead and rings the doorbell. I want to send something. Here's the Fibre Channel NVMe packet will go out. It'll be built into the SQ. It'll go out. The storage adapter will receive it. It will generate an interrupt. Remember, so it is receiving, and it'll put that packet inside one of the IO queue, where that's where the data is sitting in there, and it'll go ahead and it will tell the controller will go in and will fetch the data and it'll write it to that particular flash. Again, in NVMe world, everything is written with namespaces, and there can be different type of namespaces in there. They are like active namespaces. They could be allocated and deallocated. So I'll talk about it a little bit later on. All right. So now I talked about, this is the IO controller. The controller I'm showing here is the IO controller because it has storage behind it. There's another controller within NVMe, which is called discovery controller. Now, IO controllers, there could be hundreds of IO controllers within a given subsystem. Now, there could be multiple discovery controllers also, but usually there's one discovery controller. This discovery controller will tell the inquiring host how many IO controllers are in this subsystem in there. And the way it tells it through the log page. The host will ask for the log page 70, and then it will tell you that this is the controllers I have behind me, and IO controllers, and you can access these IO controllers. Now, IO controllers have the namespaces behind it, and those namespaces get identified by the CNS, controller namespace structure. One of the bytes is called 02. That explains how this namespace is identified. Now, namespace within within NVMe, it's a very elaborate system in there. So we all understand LUN and namespace, right? LUN is SCSI, namespace in NVMe. But the namespaces are grouped within NVMe to a bigger thing we call NVM sets. And then NVMe sets are grouped into yet another bigger hierarchical called endurance groups. And then endurance groups are grouped under another bigger hierarchy called domains in there. So this is a huge, very elaborate system of there. If somebody wants to go and design how they want to access NVMe storage, they can do that. So now what happened is underneath the thing is that, as I said, NVMe is seamlessly mapped. This is the beauty of the T11 committee. What they did was NVMe consortium did not write the transport mapping spec. The T11 committee wrote it, and they call it a Fibre Channel NVMe spec. So they took the existing protocols like FLoggy, PLoggy, and process loggy and all that. They added few of them in there, LS, CAS, and all those things, and connect, and then I'll talk about this thing. So what happens? Let's start with the fresh. When you connect the host to the your storage array, the first thing happens is that the host automatically, this is the beauty of the plug and play, right? Fibre Channel is plug and play. It's unlike, any other transport where you have to have some kind of automation done through Ansible or through Terraform or some or software defined controller. Fibre Channel is automatic. You connect the host in there, immediately floggy will happen. The FCIDs will be assigned. It's automatically addressing in there. Buffer to buffer flow control is a lossless thing. Also, that the Fibre Channel is a zero copy. So that means that when the data goes through the Fibre Channel adapter, the CPUs does not make the operating system does not make multiple copies for the CPU. In other transport, what happens is when you get a packet in there, it will go into the memory, the operating system will take it, and then in the kernel space, and then it will make a copy to the user space. So they get two copies in there. In Fibre Channel, it takes it in the kernel, and it gives the pointer to the user. It says the user space and says, here's the application, and you can take the data right out of there. Anyway, so those are where the buffer to buffer credit come in there. It's a lossless behavior in there. And now the second thing happens is the port login goes in there. Here we're going to discover automatically that is this port capable of doing a Fibre Channel NVMe also. As I said in the beginning, you can do both things on it. SCSI you can do and Fibre NVMe on both of those things seamlessly. So if this port says, yes, I'm capable of doing Fibre Channel NVMe, and it will also tell you that behind this port, I have a discovery controller also. So you can query that what namespaces are available, what resources are available in the NVMe. And that's one of the things it's going to say, okay, so then the process login will go in, it will query something a little bit more deeper inside it, and it will say, okay, so this is the initiator port, this is NVMe, and this is the target. Of course, you have a discovery service, and it might query at that time, or it does query at that time, because sequence level error recovery, do you support that also? And that flag bit is set in that communication. As I said, NVMe works on the queuing architecture. You have to have an admin queue to start with it. That's a queue number 0. But in order to create an admin queue, you have to create an association first, NVMe, and this is where the NVMe association will be done. And and this is called, link services, the create an association command goes out in there. And then what happened is and this is a trace. By the way, I've never taken Fibre Channel traces in my life. I've been involved with Fibre Channel for 20 years. I just took because it's all plug and play. It always works. I don't have to know how the trace looks like. On the Ethernet side, I take trace every day. I mean, can't live without it. But I took the trace on the Fibre Channel just to look at it, how these commands are going through it and all that. So you will have this thing. You can browse through the presentation later on today. And then, okay, so it will say, okay, I'll create the association. I accept your request. And this is the association ID, and connection IDs are defined in the trace. So now the connection IDs are defined in there. Now the NVMe protocols will say, I'm going to connect. When it says connect, that means I'm going to start creating now queues. So admin queue is 0. Before I just created an association. Now actually I'm creating a queue. And the queues are always on the controller, not on the host. I'm showing you a queue on the host. This is just a reference that this traffic is going to this particular queue. So this is admin queue 00 on both sides I'm showing you, but on the host is just a reference metaphor that the queues are actually on the controller itself, NVMe. And by the way, keep alive timers are used in NVMe. In Fiber Channel, we have a much better method of making sure that what is things are going in and out in the Fiber Channel fabrics, and we all familiar with SCR and RSCNs and all those things. So we use that. Even if you set a keep alive timer, like in this Fiber Channel, I see the K12 value set to 0. We just ignore it in Fiber Channel because we have better ways of doing things in there. All right. So now the connection is established, and now request response says, okay, I have connected it. The next thing is the properties. Now there are three things within NVMe. There is the capabilities, there is properties, there is the features. So the properties is that what kind of a property this controller has. So for example, on discovery controller, this controller has what properties? All right. So this memory on this particular flash, there's a memory on that, there's DRAM on it also. That's where the controller property sits for that particular flash in there. That memory, because it's an MMIO, gets mapped into the CPU memory. So CPU puts up an offsets, that what offset starts this controller property. So there in the properties, in this controller properties, you have there's called a cap controller properties. Then there's a controller configuration. Caps supports what kind of a command sets are supported. Controller configuration area in there shows what are the IOQ size. Then there's a controller status property in there, whether the controller is enabled or not. And then there's the base admin queue, where the admin queue is going to start the base address of the admin queue. That's what it is. It is also shown in there. Now, going forward in there, once we get that, this is this, okay, I go ahead and, as I said, in the controller configuration, I enable the controller. Now controller is ready to accept the NVMe commands in there. And, it says, okay, make the controller ready. It says, okay, controller is ready, RDY. And now it's going to ask for what are the IO controllers behind this thing. And it's going to say, it's going to issue a log page 70 command in there. So there are different type of log pages also. There could be a log page, 70, which tells you what different IO controllers are behind it. And then it will say, okay, this is the 5 different IO controllers, and these are their NQN names that will be shared. And then the host, then what can it do is, once it gets that information, and that it'll get also in the log page, it will tell you what are the different ways to get to that particular controller. There could be multiple paths to it, right? Or different transports way to get there also. And what is the subsystem names and all that. So all that detail where the IO is supplied in the NVMe log page via the discovery controller. That's the sole purpose of the discovery controller, is just to tell that there are IO controllers in there. All right, that's fine. Now the host is going to create an NVMe session with the IO controller. So it's going to go through the same steps in there, create an association connection ID, create the IO queues in there, NVMe connect command will get issued in there. Now you see when everything is running, the IO controller will have a one admin queue pair setup, and then multiple IO queues. Depending upon how many cores you have, that many number of IO queues will be there, right? So this is the architecture, what it looks like. And then NVMe also can issues an NVMe identify command. And in that case, it is, as I said early on, it's a CNS02, which says active namespace list, controller namespace structure. And then that active namespace list will come in there. And then the host can end up writing to the that particular thing. And then it goes to the flash. It goes to the flash to that namespaces have namespace IDs behind it. And that it'll write to that namespace ID, and that will end up writing into the logical block addressing. And that's how you end up writing to that particular area in the flash. And later I'll talk about it, that we can even partition the flash into different ways to make things more optimized to reduce the tail latencies. I'll talk about those zone namespaces and flexible data placement of flash ideas in there. But, and this is here I'm showing you how the namespaces IDs are discovered with what connection ID. This is an NVMe. Again, as you notice that on the top, it is the fiber channel frames, fiber channel headers. And then the NVMe is in the payload and embedded inside the after the fiber channels. And here the details starting showing there. Now, this is the diagram which I went through different specs on fiber channel and NVMe. I conceptualized this diagram based on the architecture as I studied, and I took the traces in there. But it gives a very, very, very clear picture how the data goes from the host to the storage array, and what different things happen, and how it can access that particular logical block addresses. And later on, I'll talk about it also, that even though SCSI use LBAs and NVMe uses LBAs, in object stores, people use key values. So somebody said that, oh, why do we need the logical block addresses? Can we use key values within the NVMe? So there's a different command sets for that, and different storage SSDs, called key value SSDs. I'll talk about it in there also. So in that case, it will not be LBA, it'll be key value, how the data is stored. And so summarizing what I just talked about, it below the hood, what is happening is that the host comes in, and this is all automatically happening. As I said, beauty of the Fibre Channel is plug and play. Whether it's the past technologies, FICON, it goes into Fibre. By the way, FICON is not NVMe, right? It's just a SCON protocols command channel mapped into Fibre Channel. So Fibre Channel, the beauty of the Fibre Channel is that it is also payload agnostic. It's taking the mainframe payload and a single byte commands and the controllers and the channels, and mapping it into Fibre Channel. It can take the SCSI as a payload, maps into the Fibre Channel, and it can take the NVMe as a payload and mapped into the Fibre Channel. So all those F-loggies, P-loggies, all those are basic Fibre Channel things. And after that, we said this is the PR login, where we figure it out as the Fibre Channel NVMe. We start to create the queues. Before we create the queues, we have to create an association that, are you okay to create the queues? And then the first thing we do is to create an admin queue, because in the admin queue, you can send up all the commands to do the other stuff. If the admin queue is not there, you cannot have the IO queues, and you cannot transfer data, because admin queue is the one where all the commands go in there. IO queues only does the IO commands, read and write. Admin queue does all the setups and admin commands in there. And then, of course, as I said, you can do the properties, get the controller properties. That property sits on the flash DRAM in there. And those properties are like, what command set it supports, where's the IO queue starts from, the base addresses and all that things in there. And then, of course, once the IO queues are established, admin queues is first established, then we can send an identify command over the admin queue, and it will go ahead and it will log 70 and will provide all the details. And then we go ahead and create to the IO controllers. Same process happens. Identify what namespaces are, and then we can start to write. So all that happens automatically behind the scenes in there. NVMe, as I said, brings you many advantages, and I'll go over those advantages in a second. If you do want to look in the packet deep inside, I will highly recommend to look at the T11 FS6 spec in there. All the packets headers are described in there. I try to quickly put few things in there. Point to note here is that if FCID in here is 28, that means it's the NVMe. And if you look down in there, this is the NVMe command header looks like. And if I look deeper inside this NVMe command header, as I said, 64 byte. And here's the what type of a command it is, NVMe, and then command ID, namespace ID, if there's any, and then the starting logical. If you're writing something, there's an SGL descriptor in there. So this is how the NVMe command looks like. And then when the data is transmitted, the beauty about this Fibre Channel is that it utilizes the best of best for everywhere. So when the actual data goes in there, there's no NVMe command going on. Now it knows from where's the starting block of the the logical block address to the and how many blocks you have to transfer. So once that is exchanged, then the data goes through, and the data goes through is an FCP data in there, and this is very clearly written in here. So that is the architecture in there. Now next 10 minutes or less, I'm going to talk about so what are the benefits? What do I do? And then Nishant is going to come in later, talk about it, how to adopt NVMe on your existing fabric, and how the vendors are doing in their support and all that. So let me give you some NVMe advantages. Everybody knows NVMe provides you higher throughput and higher IOPS, like we really need in Fibre Channel. We're already happy with 16, 32, 64 gig. But, the world is changing very fast. There's other applications, enterprise applications, especially on analytics, demanding more and more throughputs. Now with AI, ML, today it is done mostly on the file and the object, because the people now we're trying to integrate that with the block storage, and the Fibre Channel can play a key role. And I'm pretty sure Nishant will talk about it, how that's being adopted with AI MLs, the Fibre Channel with NVMe especially. But anyway, so NVMe being directly mapped into the PCI bus takes you the speed to the maximum of the PCI. So today the NVMe SSDs are like 4 lanes. So if you take PCI 5, 4 lanes, that gives you, the 128 gigs. So that's like a theoretical limit. So practically you get about 100 gigabits of the throughput out of that particular SS. That's huge. If you compare it to the legacy ones, SATA or, the SAS, you don't get that much. And, and those standards are not going further anywhere. And it is all NVMe PCI taking over. And next generation of the PCI bus is CXL architecture, and this NVMe PCI seamlessly maps into it because CXL is backward compatible. It is the same PCI transport. They're just adding the memory and the messaging architecture on top of it. So better performance is given with NVMe. But do you know that NVMe can also reduce your tail latency? You know what a tail latency is? That when you have all your IOs going through, if one IO is stuck, the whole flow completion timer goes up because that particular last IO did not come through. And the last IO did not come through because the way the flash stores the information is that it randomly stores for all application. So that means if a particular block of the flash is doing some garbage collection, so it's inaccessible to the outside world, all the applications data written on it will be blocked for that particular milliseconds or microseconds. So with ZNS, zone namespaces, you create different zones. Nothing to do with the fiber channel zones. It's just sections. You create different sections on the flash. They call it zone. They use the term out of fiber channel anyway. So that you can write each application to its own zone. So if that particular section or zone is doing garbage collection, only that application gets impacted, not the other application gets impacted in there. As I said in the beginning, that Fibre NVMe can also, do the, each separate exchange ID is created on each queue in there. So if you have 132 queues, you have 132 different exchanges going on. So there's a lot of load balancing going on, exchange bill load balancing going on. So what happens if any of the sequence gets out of sequence in there? So within FC NVMe version 2, which is out, for a while now, they added a command called flush. Now, this is a BLS level, fiber channel level command. So let's take an example. The hosts issue some command, and the NVMe fiber channel adapter will turn that into an NVMe command and send it out to the target, and they will start a timer, the flush timer. Usually, like it's a 2-second. You can configure the value, and then if there's no response come back, flush command will be issued by the initiator. And with the flush command, I gave you some of those internal packet architectures. Again, look at the FS and LS spec on the T11 for details, and also FCP, spec. So the flush response will say, now mind it how it tells it. It's a little bit tricky. Again, the beauty is that we don't have to worry about it. It's all done automatically. The flush response will say exchange is open. That means, exchange is done on the command basis mostly. Every new command start a new exchange is open, sequence IDs, start. So every exchange is open, but the NVMe target NVMe port holds a sequence initiative, and target is this guy who received the command. So that means he's saying, okay, I got the command, I will reply back, not a problem, there's no problem, I got your command. So there's nothing, no recovery is required. But what happens if that command doesn't reach and the timer expires? 2 seconds later, the flush command will go in there, and the target will say, wait a minute, I don't have any exchange open, what are you talking about? And then the initiator will say, oh, so that means I did not got the first command did not go through. So it will retransmit the command in there, right? And this is how it happens. Now, what happens if the response is lost? Again, the reason as I'm talking about this flush command is because if as absence of the flush command, it will have to time out. And as it's within the T11 fiber channel, they talk about it, the big hammer. That means, if it's times out, and that timeouts could, at a higher level could be like 30 seconds. Now, here we're talking about NVMe doing in sub-seconds and milliseconds and very less time, quickly performance. But if you have to wait 30 seconds, that defeats the whole purpose of having an NVMe, right? So this slur, the sequence level error recovery with this flush commands and the whole protocol which I'm describing you makes the error recovery in fraction of a second in there, much faster than. So it's almost like 10 to 12 times faster than what you get with the previous versions without slur in there. Slur came out with the FC-NVMe 2, right? So that's where it is. So what happens if the response did not come in? Okay, the response did not come in, flush times, the NVMe command timers time out, and the flush command will be issued. And now this guy is going to say, yeah, I received the NVMe command. That means the sequence is, it's open, but that means the initiator is holding the sequence initiator because this guy initiator transmitted the command. So that means, that means I did not, that means I need to suppose to send something out because the initiator is expecting something. Now, how does the initiator tells the target you have to send something out? So he sends another command after receiving the flush response. He'll send a sequence, retransmit. He says, "Hey guys, please send that last. Here's an SR response. It'll tell you what it'll tell to do that. So it'll retransmit the last response, whatever the response was in this case. So that's how they take care of it if the response is missing in this thing. Now, what about if in the middle of the data some packets are not received? Oh, okay. So now the command went through it. Okay, the target said, "Okay, send me the data." This is NVMe write going in. The host starts to send you the data, and let's say first packet does not go, second packet doesn't go, and then data comes. So the target receives out of sequence. So you say, "Wait a minute, what happened? I didn't receive the other sequence. What happened in there?" So this is now responder has detected an error. So there's another in Slur, there's another command they added is called RED. So responder error detected. So once they detect that it's out of sequence we've been receiving in there, we're missing some sequence. You can receive out of sequence, that's okay because we can rearrange and all that. But if you're missing a sequence, then how do you rearrange, right? So RED will be issued. RED issues in there, then the initiator will say, let's do a resequence transmit. That means send me another transfer ready and I'll go back to 0 and I'll transmit all the relative offset. I'll transmit the data all together, all data again in there. So this is like if the target receives any problem, it can request RED in there. Again, as I said, with sequence level error recovery, it does not bother the upper layer protocols, and that means NVMe. Fiber channel itself take care of it. So guys, this is the third advantage to go to NVMe because your error recovery becomes very fast. The first was the performance goes very fast. Second was you can reduce the latency. Third was, your error recovery is much faster now. Look, all these benefits in there. Let me talk about fourth advantage. What about if you have an application that is very key value, like RockDBS or something, Redis or Ceph, some kind of MongoDB, something like that. In those database-oriented applications, they write with key value. But when you go to NVMe, it writes with LBA, right? It writes with LBA. So there is a key value replacement of LBA within the NVMe spec is called key value. And so they write directly with the key value on the flash. So that means a database application writing with the key value will not require any translation from key value to LBA. It will directly write into the database. So that makes those key value applications much faster. But mind it, not every NVMe flash does it. You have to read the NVMe SSD flash, key value NVMe SSD. So you can Google it out. You can find out a few vendors offer it today. There's another beautiful thing about it is that, as I said, NVMe is mapped into the PCI bus. It is very fast. But what happened is PCI is mapped into the CPU. Right? PCI is the CPU memory in there. So every time any interaction happens, let's say NVMe read command comes in there, it will tell the controller NVMe, which is over the PCI bus, CPU is involved, and then the controller will say, okay, here's the data. It will tell the CPU again because the memory of the CPU, that's where the data is pushed out, and then data will go out. So you notice that the CPU gets involved quite a bit. So what if we can do this thing? NVMe read commands comes in, CPU gets involved, it tells this is the data is, but what if we tell the host, give the direct, because this is a memory mapped storage, NVMe here, that direct starting address and ending address of where in the memory this data is mapped. So the adapter and the host can directly access it without involving CPU. This is called CPU offload. But mind it, you have to configure this. Your application have to be aware of it. So it's just not plug and play. Your application has to be written with CMB feature of the NVMe in there. So that was the fifth advantage. Another big advantage is going to come out. I'll take another couple of minutes to wrap this up. Is that sixth advantage is, actually this is the final advantage, is that computational storage. In other words, today, as the data has been zettabytes and data is stored, everybody is jumping. A precursor to the AI world was the analytics, right? You want to analyze the data and you want to take some decisions on it, how many a particular product is sold, what color this is. So whatever analytics you want to do it, the way to do that prior to this computational storage, the spec is not out yet from NVMe, is that you move all data to the data lake outside. So you use the transport, move out, and then you do analysis of the analytics on there. Then you give the results to whoever is asked for that. What if, because NVMe storage array is holding the data, what if you can run your analytical application right on the storage array? So, okay, so then you need an NVMe command to tell what analytics program you want to launch. So those are the few technical proposals on the table, which this computational storage will come out in a spec, most probably in the next versions or whenever they decide to. It will launch that particular application on the storage array itself. It will fetch the data from the flash into the memory. So this is called memory namespaces and all those things. And then it will analyze with that program analytics, and then it will give the result back to whoever asked for it. So without data stepping any foot outside of the storage array, you take it out in there. Beautiful talk in there, right? How far are we done in there? I talked a lot about it. I talked about the architecture. I talked about the different applications. 6 applications I've given you. I have not even touched the namespaces. Is huge in NVMe. There are dispersed namespaces. There's asymmetric access namespaces. There's the disaster recovery. So a lot of things I've worked on. How the data are stored. We will talk more about it in some other FCI presentation. But I'd like to invite Nishant here and have him share how well NVMe is adopted, what are the challenges. And so, Nishant, please take it.
Hey, quickly before we move on, Nishant, for just a second, and Kamal, I think you pointed out that we actually need to have another one of these sessions, a version 2. But a couple of quick questions I'd like to throw in that are very germane to what you just talked about. The one that's most prevalent here is the slur advantage only applicable to the FC application of NVMe, or is that also available in Ethernet TCP based implementations?
No. So this is again, I said the beauty of this is the Fibre Channel from day one is plug and play automation. So they continuously think how to make things automated in there. So slur is applicable to the Fibre Channel NVMe 2 version. The Fibre Channel NVMe 1 version also has a capability to improve, but it's not as good as slur. And without NVMe, Fibre Channel also has timers out, timeouts, and all that. So not as good as the NVMe 2 version. So slur is only to NVMe Fibre Channel. And I think somebody else can answer the question, but on this panel. But that is being backported into the FCP 4 or 5. Also, the slur capabilities. Yeah.
And for the rest of you who've been asking some fantastic questions, we will get to some of these by the end of the presentation. If not, we will actually be getting a Q&A and getting these written out and back to the community at large. So, Nishant, take it over, buddy.
Hey, thank you. Thanks, everyone. What a whirlwind tour, Kamal. I think it's just amazing how you put things together, and it's been so informative. But so, guys and people, now that you've kind of learned a deep dive into the technology, kind of how the sausage is being made, it's time to talk about when we talk about FC-NVMe, how has the adoption been? What are the use cases? And what are the different pieces of the puzzle in terms of ecosystem that we need and to get FC-NVMe adoption right, and what is their current status? And I know there's been a bunch of questions related to these, and I'll try to answer them as we can just go about. So first, I would say that FC-NVMe adoption is on the rise. Based on current estimates, we expect that about 10% of fiber channel connectivity today is going over NVMe, which is we are using FC-NVMe from a server going through a switch to connect to an all-flash array. This is expected to grow to about 25-30% in the next 3 years. And that is a significant growth rate. And the question arises, what is driving this change? So there's a fair question to be asked. Hey, the standard was done, let's say, 4 or 5 years ago, right? And where we are today, and probably the first products came out, let's say, 3 years ago. We are only at a 10% adoption rate, and what is driving this adoption rate to go forward so much, and we'll talk about that in a second. But before we do that, if you look at FC-NVMe, right, the people who are primarily adopting FC-NVMe is the people who are deploying all flash arrays, people looking for the low latency, extraordinary efficiency, scale, performance, and things like that. So you look at financial applications, business critical applications, real-time analytics, huge databases. Like Kamal said, the beauty about FC-NVMe is that things are automating. People have put in a tremendous amount of thought to get this simple and easy to use, and Kamal talked a whole bunch about it. FC-NVMe is fully backward compatible with FCP SCSI, which means that if you have 2 different storage arrays, one does NVMe and one does SCSI, you can talk to both of them through an HBA and a switch, right? And it's, in fact, you can do it concurrently. So now let's talk about the ecosystem. And when we do talk about the ecosystem, there is a couple of different pieces to it, right? There is a hardware piece and there is a software piece. And those are my next 2 slides, right? So the hardware piece, there is a Fibre Channel HBA, and the 2 vendors, both Broadcom and Marvell, have Fibre Channel HBA 16, 32, 64. which do support FC-NVMe. It's just the same HVAs that you have used. If you update their software on them, you will get FC-NVMe capabilities. Okay, and you can do it concurrently across any of the ports of this HPAs. Similarly, for the switches coming from both Brocade as well as Cisco, these switches support FC-NVMe. In fact, switches did not have to change a lot to support FC-NVMe. So even if you have an older switch, please go ahead and use that to transact over FC-NVMe. And last but not the least, storage arrays. From where we are today, almost all the major vendors in their all-flash arrays support FC-NVMe, right? And I have put down a list here. This is definitely not inclusive, but there's a, if you just kind of look up FC-NVMe interoperability matrix, you will find a huge list of all the different storage arrays that support it. From a hardware ecosystem, right, it is pretty complete, okay? Now let's talk about the software ecosystem, and this has been developing recently, and I'll quickly kind of journey you through this. So there's a lot of operating systems, but I've just picked the top 3 most popular operating systems. Certainly they are not listed here in their order of popularity, but just in a random order. So let's first look at Linux, right? A popular operating system, FC-NVMe is fully supported. It has been supported for a while, starting from RHEL 7.8, 8.0, and all the kind of versions after that. Similarly for SLES, starting from 12 SP4 and then onwards. Now, if you realize that in software, it is not just about putting a FC-NVMe driver into this operating system and calling it a day. Okay, there is a bunch of other things that our customers expect us to deliver when we have to enable FC-NVMe on these operating systems. And what are those, right? We need multipathing. You know, Kamal talked about all the fun things there. We need boot from SAN. All of that stuff has been supported in Linux. So Linux ecosystem is pretty complete, pretty rock solid. In fact, it has been the furthest of any other operating system in terms of getting to FC-NVMe support. So if you are running Linux, any of the newer versions, you are all set. Okay, let's talk about VMware ESXi, popular hypervisor. There has been a journey within VMware ESX. Support for FC-NVMe started with ESXi 7.0, which must be like maybe 3 years ago. And, you know, sometimes my timeline is a little blurred. But more importantly, right, between 7.0 and then 8.0 and 8.0 update 2, which is the more recent one, there has been a lot of new things added. For example, I think in 7.0 update 2, there were a lot of enhancements done for NVMe to increase the kind of number of namespaces, the number of ports, and kind of scale to that. Within ESXi 8.0, end-to-end NVMe was supported, which is kind of having the entire stack transact on NVMe rather than doing translations. And the most important thing, very recently, ESXi 8.0 supports vVols with FC-NVMe. Okay, that has been a huge support delivered by VMware that has enabled our customers to look at migrating from Fibre Channel to FC-NVMe. Many customers use vVols, and I don't have the time here to talk in detail about vVols. Many customers use vVols, and not having vVols support with FC-NVMe was a significant impediment in adopting FC-NVMe, but that has gone away with the ESXi 8.0. There are other more interesting things coming up in future versions of ESXi 8.0, which will further enhance this. But today, ESX ecosystem is fully ready, including multipathing and boot. Talk about Windows, and Windows, I'm talking about kind of bare metal Windows. There is currently no native support for FC-NVMe. There is support provided by HBA vendors, Broadcom and Marvell to provide an emulated mode. It does not having native support in Windows does not impact. Let's say you had a Windows VM on top of ESXi, you had Windows VM on top of KVM. It does not matter there because the base operating system already supports FC-NVMe. With that said, a full hardware ecosystem and a software ecosystem across Linux and ESX that is today complete with ESXi 8.0 and the newer Linuxes. Adoption for FC-NVMe is only going to grow from here. With that, I'll pass this over to the next speaker. And please, Mark, talk us about performance.
Great, thank you, Nishant. Up to this point, we've heard a lot of great information about the architecture and the reasons why FC-NVMe is so performant and has so many advantages. What I'd like to talk about now in our last few minutes is a couple of examples, real world examples of how solutions today can help improve performance of the applications that our customers are looking to use and really need the extra performance that's available with FC-NVMe. The first example, and this is a question we received online just moments ago, is regarding performance of FC-NVMe in AI. It's very common with AI ML to really require extra performance, and FC-NVMe really helps here. We actually covered this in a previous Bright Talk webcast earlier in the year, and it's available in our library, either within Bright Talk or on YouTube, where we discussed in depth NVMe's performance advantages with AI ML. In this example, we actually compared that with traditional fiber channel, so it's FC-NVMe versus traditional FCP on both containers as well as virtualized server environments. And in every case, whether it was with containers or with virtualization, there was a significant performance advantage in reducing the training time of the AI model. Here we can see it ranges, depending on the size, it ranges from the teens to up to 54% in reduced training time. So very significant. I would recommend everybody go back and review that Bright Talk webcast that we did earlier in the year. The final example is a very common workload that we see Fibre Channel utilized in with all-flash arrays, and that is large corporate databases where we have structured data, and there's a very high transaction rate on those databases. Simply by choosing the FC-NVMe option, there is a significant performance advantage that we typically see there. In this example, there's a benchmark run very similar to the Transaction Performance Council TPC. It's called TPROC-C, that runs on HammerDB with an all-flash array. And just by choosing FC-NVMe, the transactions per minute time, as seen from the database front end, this is what the users see, is 53% faster using FC-NVMe. In terms of store procedure latency, that is also reduced. As Kamal mentioned, there's a significant latency advantage with using FC-NVMe. And in this case, we can see this at the front end of the database being 58% faster. And then there's also an advantage in terms of CPU efficiency. So the host itself, the stack being more efficient, all helps to reduce the CPU utilization on that device, allowing it to be utilized for more VMs or more other activity or run other applications, or just simply save on cost of that machine. So it's a significant advantage there. If you want to find out more about this, I suggest just searching online. A number of vendors have results very similar to this. A lot of third-party data is out there as well. But we see it universally across, no matter who the vendor is, what storage array you're using, that there's significant performance advantages when using FC-NVMe. And with that, I think we're near our time limit. I'll turn it back over to our moderator.
Thanks, Mark. Fantastic presentation by all three of you. One question that came up, I think it's worth asking right now, is we have a question regarding the minimum FC-NVMe speed supported or qualified. I don't believe there is a minimum speed qualification. It's predicated on the speed of the FC fabric employed. Is that correct, Kamal?
Yeah.
That's what I thought.
There's no. Usually, when you talk about speeds, especially on the switch vendors, a lot of like 32 and onwards, there's a lot more analytics added onto it. So every speed bump, there's more bells and whistle added on it to get more deeper into FC-NVMe and all that. So you just check your switch vendors data sheet to see which speed they have those analytics enabled.
And I can say from my time I spent with the the T11 group that we're continually advancing the protocol to support these changes and advancements in the requirements for these technologies that are transiting the fiber channel fabric. I do have one other question here that I thought was kind of important, if you will, is what are the inherent security advantages to NVMe FC versus Ethernet-based NVMe?
Yeah, so I'll talk about Ethernet, and somebody can take the fiber channel. Ethernet world still, it happened to be coincidence. They're also talking on a Bright Talk right now, or they just finished a talk through Dell. Claudio is talking on it about bringing NVMe TCP security enhancements to the NVMe consortium. They're talking about making mandatory TLS 1.3 for NVMe TCP to be mandated for the TCP security, because as you can imagine, TCP is a pretty open architecture in the world that is connected all over the world. So security becomes a big concern because you don't know who else is tapping into your Ethernet network. Fiber channel, on the other hand, is very closed network, a very dedicated network. So, the security is not that bigger issue here in fiber channel world then. But of course, we have fiber channel security protocols and all those things too. FP, SP protocols, security protocols.
Yeah, and generally speaking, because of the nature of fiber channel and the way it's structured, it is just a generally more secure environment. And because it is a storage backbone, it's storage fabric by nature. Ethernet, of course, is very malleable and applicable in all sorts of different areas, where fiber channels, main reason is to be a secure storage environment. So
yeah, I mean, the fundamental, David, the fundamental is the zone is not there. The host won't even access the fabric fiber channel. In TCP world, you can just connect any host to the any fabric.
Yeah. So, as I said earlier, we will address all of these questions and put out a part of the follow up is to address all these questions and to blog them accordingly. We do really value the feedback of the listeners and the viewers of this webcast, so please do rate this event where possible. As I said, we will post the Q&A blog on the fibrechannel.org website, and you can take a look at the library of FCIA on-demand webcasts at the URL listed on this slide. It includes pretty much everything that you could imagine about fiber channel, and some fantastic speakers and some excellent knowledge base that's available in there for those of you that are either trying to refresh your knowledge base or gain some new knowledge into fiber channel itself. Follow us on the FCIA News at FCIA News for updates on all the relevant socials. And with that, we ran a couple minutes over. I thank you on behalf of our speakers. We really appreciate your viewership, and we hope that this came across with some great information for you. And with that, I'll let you guys have the rest of your day back. Nishant, Kamal, Mark, thank you very much.
Thank you, guys.